All right, so we figured out that using line length is great if we want to figure out the distance between 2 points that are horizontally on the same line, or the distance between 2 vertical points that are on the same line. But what if we wanted to figure out something like this? Check out my picture over here. So I have this point here, 0, 4. So when x is 0, y is 4. And I also have a point here when x is 3, y is 0. I couldn't use line length as it stands now to find the distance between these 2 points. All I could do is find the distance between 0, 4, and 0, 0, and then 0, 0, 3, 0. So drawing a line from the center of one object to the other, as in this point to this point, would create a right triangle with sides A, B, and C. A and B are the vertical and horizontal distances, and then we call C the distance between the two coordinates, kind of like the do now. So we also have to think about the hypotenuse here. Thinking about the hypotenuse, which is the length of C, consider our problem from earlier. If I have a circle here with the center at 0, 4 and a circle here with the center at 3, 0, I want to talk about collision detection again. So if we remember back to this slide in my PowerPoint here, we know that the circles will overlap when the distance between their centers is less than the sum of their radii. So remember, the distance between these centers was 1, 2, 3, and the sum of their radii was 1 and 1.5. So going back to this, I have a center here and I have a center here, so when are these going to overlap? So we have to use some Pythagorean theorem. As a reminder, I have all these cool slides for you to look at, so check this out. For any right triangle, it's possible to draw a picture where the hypotenuse is used for all 4 sides of a square. In the diagram shown here, the white square is surrounded by 4 gray identical right triangles, each with sides A and B. The square itself has 4 identical lengths of side C, which are the hypotenuses for the triangle. If the area of a square is expressed by side times side, the area of the white space is C squared. So notice, just as their picture, you got A, B, C all around. So what they're saying is you can multiply C times C and you would get the area of this white triangle. What else do we have to say? So by moving the gray triangles, it is possible to create 2 rectangles that fit inside the original square. While the spaces taken up by the triangles have shifted, it hasn't gotten any bigger or any smaller. Likewise, the white space has been broken into 2 smaller squares, but in total it remains the same size. By using the side lengths A and B, one can calculate the area of 2 squares. So, looking here, I could make 2 rectangles with those gray triangles that I had previously. The smaller square has an area of A squared. The larger square has an area of B squared. Since these squares are just the original square broken up into 2 pieces, we know that the sum of these areas must be equal to the area of the original square. This is basically a long way of talking to you about A squared plus B squared equals C squared, and you're already an expert on that because we already did Pythagorean theorem. The more advanced version of Pythagorean theorem is really the distance formula, which is going to be on the next page of your packet. So as you're looking at that, remember all the things you know about Pythagorean theorem. Here we go. If we know A squared plus B squared equals C squared, in order to get C squared to just be C, we have to take the square root. So wouldn't it stand to reason that A squared plus B squared all under the square root here does equal C? That's all the distance formula is talking about.